Well, what's this crazy thing? It says Turner. It is a Model 690 spectrophotometer. So what is a spectrophotometer? It is a thing that measures light and measures the spectrum of light. This particular thing was it's fairly old, and it was for measuring so if you have white light going through a test tube and you have some type of colored liquid in there, then it would measure the spectrum on the other side. So it would measure the absorption and transmission of light through a liquid. And so it had a display here for frequency, wavelength, and some type of number on the other side. The number could be percent transmission, so at a particular wavelength, how much light does it transmit? A, C, and F? I don't know. Sorry. So how did this thing work? Well, there's this little thing on the top, and you can put a test tube in there. In fact, you don't call it a test tube, I think you call it a cuvette. And it is a square test tube. It actually has, I think this is made out of quartz, and it has two clear sides that are parallel to one another, and you fill it up with liquid, and then you drop it in here, and then light goes through it, and then you measure it. So that's what it did. And this thing didn't have a digital output. It had basically, I think, it hooked up to a pen plotter. So it would plot you a graph versus wavelength. So it would output two voltages, and it would drive a pen plotter. I think that's the way it worked. Anyway, all it had was this number pad and this funny display on the front, and that was it. Well, I wanted to see if I could steal some parts out of it. So I was interested in building my own type of spectrophotometer, and I thought, well, I could start with this and maybe steal a couple parts out of it, and instead of reinventing the wheel, I got this for, I think, $50. And so I thought, I'll open it up, pull some parts out, throw the rest away, and I'll be done. This thing here, I pulled it out, and so this is where the light goes through through that bottom section there. So if we pull our little test tube out, it sits down here. So about the bottom third of the test tube has light going through it. And so if we take the top off of this thing, we'll see some stuff inside. Let me move the camera. All right, so it has a power supply, AC power supply, and it has a fan here for cooling. It has kind of a motherboard with two card slots in it. When I bought it, there were two cards in it. Just a second. One for an analog circuitry and one for digital circuitry. And I pulled those two cards out and wasn't quite sure what to do with those. And then I said, okay, well, let's see, where's the goodness? The goodness is over here in this box here. There's a light bulb over here, a halogen light bulb, and so it outputs light, and the light travels this direction. And there's a mirror on this side, so it travels this direction, hits a mirror, it travels back this direction, there's another mirror here. And then it goes through a diffraction grating, and that diffraction grating can be moved to select a wavelength. And then, let's see, the way it works is the light comes through here, bounces off the mirror, goes this way to a mirror back here. It's actually a diffraction grating mirror. And then, so the light goes bang, bang, and then it goes this direction. And then it goes through the test tube, and then it hits a photodetector up front, and then the photodetector goes into the some amplifier and circuitry and stuff like that. So that's the way it worked. The mirror's angle can be changed with a motor. Here's a stepper motor, and this little flexible shaft here goes to a section where this moves in and out, and it moves the mirror accurately, or the diffraction grating accurately. And I thought, great, I'll rip this all apart and everything. Then I discovered, oh, there's a filter wheel inside here too. There's a second motor, spins a filter wheel. There are like 7 different filters inside this thing. Oh, that's pretty cool. And I thought, well, maybe I can hack it. And so I designed this card and got the thing working. So what does the card do? The card has 2 motor controllers for this stepper and this stepper, and it has an A to D, so it can measure the voltage out of the photodetector and amplify it, digitize it, and then send it to an Arduino, which is here, and then the Arduino can do a bunch of magic. And I thought, okay, well, then I want to be able to display that information, and way down here I cut a hole in the front panel and I put in a display. And so the thing actually works now. I built this about 4 years ago, so I don't quite remember everything. But let me try to get you a better shot of my board. All right. So this is the board. I have 4 switches to do various functions. I have the Arduino Pro Nano. I guess it's a Nano. And then I have a couple cards that you can buy off of eBay. This is a, I think it's an 18-bit DAC. It's a I2C 18-bit DAC. And then this is one of those motor controller chips, IC circuits, and another motor controller IC circuit. And that's it. So control one motor, control the other motor. And the way these work are a direction and a pulse, so those don't take up many lines. And this is I2C, so it doesn't take up many lines. And there might be a couple other things in there. But that's basically it. The hard part was reverse engineering everything. So I needed to figure out what voltages came from where and what ranges they had. You know, the motors were easy. I could just tie into the cables off the motors. And there was a couple other things that I needed to know. I needed to know this thing moving in and out. There's a opto switch here. So there's a post here, so you can home the thing. You can move this back until you photo interrupter. That's it. You can interrupt here, and then you start from 0. And then I could count number of turns, and then I could measure the color of the light that was going out of this thing. This is called a monochromator. The light out of here, and I noticed that right around here it was blue, and then green, yellow, red. So the visible spectrum was kind of in this range as this post moves from here to here, and then it went from about 300 nanometers here to about 1,000 nanometers here. So that's the usable range of this thing. One of the nice things also was the light bulb that's back here was being run by a controlled voltage, so it stayed stable, and that controlled voltage came from down here on the motherboard, so that I could leave that alone. Let's see here, let me swing you around the side here. You can kind of see the output of this thing. There were analog output and RS-232 and printer. I don't think the RS-232 was in there. Maybe it was a Centronics printer. So maybe this thing actually just printed a table of numbers. Maybe that was it. I think it just printed a table of numbers. And you could hook up a pen plotter with the analog output, but it wasn't. Didn't have X, Y. It only had Y. Yeah, so it's pretty crude. It does have some type of voltage reference. So there's a couple voltages that I could use for my circuit. But let's turn it on and see how it works. All right, turn the power on here. So here's my little display. It says homing filter wheel and homing monochromator. So if we look back here, the monochromator is moving slowly to the right. It will home and then it will go out to 300 nanometers and it will stop at 300 nanometers. And the system is now ready. The system is now reading some, it says it's at 300 nanometers. It's measuring 26307 bits out of the 18-bit DAC, which is 4.79 volts. There's light getting into the top here. So if I put my hand over that, the numbers go down to 1306, which is 0.25 volts. So bright light, dark light. So in order to use this thing, we'll put the oops, sorry, you didn't see that. I took the cuvette holder, put it in here. Now it's measuring low numbers. So the first thing we're going to do is run a reference. So it's going to measure the light with nothing in there and then call that 100%. So it's kind of a calibration routine. We'll call that reference. There's a button back here called reference. I'll push that. So now we have a graph from 300 to 1000, and we're measuring the light through the system as we step the monochromator. Now this will take a second. All right, so now it has to go back home. So it's running the monochromator. You can see it moving back to 300. Okay. So once we get back to 300. That's all good and done. All right, now we have a button called measure. Let's hit the button called measure, and hopefully, if everything's working correctly, we'll get a line at 100%, and it should be 100% everywhere. So it's taking measurement. It's stored that other curve in memory, and then it's subtracting all new measurements from that reference and doing a division and calling it 100%. It is a little bit tricky to get that all fit into an Arduino memory space, but with a little tricks here and there, I got that to work. So basically, it's doing that. So let us finish its thing here. It's finished its measurement. It's 100%. And it's going back to 300. Now we can measure something now. So I have, let's see here. I've got some interesting things that we can measure. I have some strips of plastic, and I've used some art markers. And I have some red, a blue, and a green. And then I can take these and I can stick them down in the machine, and we'll measure the spectral characteristics of these inks. So So let's rearrange things here. Okay, we're back here. Let me come back up just a little bit so you can put in the thing. Okay, I'm going to open this up. I'll take the blue one, and I'll put the blue one in here. We'll put it all the way down. Make sure it's in there just by looking. You can see that the blue plastic is at the bottom, so that's the light will go through there. Now when we hit the measure button, we are measuring the transmission, and you can see that it's giving us a peak, and then it's falling. The peak's at about 470 nanometers, which is a nice blue. And then it goes down, so it's not giving us any green or red light. And then after about 650 nanometers, it starts being transparent again. Most organic dyes are transparent in the IR. So this one's very transparent from 800 to 1000. It gives us this nice blue peak. The human eye is only looking between 400 and 700, so it only sees this blue here. So we're going to go back to 0. I'll take the blue out. We'll put in a green one. Put in the green strip. Come on, you can go in there. There it goes. Make sure these are in. Looks like it's in good. All right. All right. So we're back at 300. We can do another measure. So this one is going to have a peak around 510, which is a green. And then once again, after 650, it starts being transparent to IR light, and it is transparent from 800 to 1000. So again, we only see this range here, so we see this blue light, the green light that goes through. And then we'll finish off with the red color. We'll put that in the machine. Okay. I'll have to wait for it to get back to 300. And we can do one last measure. So this is the red one. So it's going to attenuate down here at blue and green. And then there at 600 it's starting to go up. And it reaches a peak around 650. And then just stays up. So a lot of reds act this way. They just let all light through from 650 above. All right, so I hope you enjoyed that. I don't really have this documented very well, but it was a great project. There's a lot still I could have done with it. There are different filters in here that allow you to use different frequencies. I just kind of chose the filter that seemed to be transparent, sort of in the range I was interested in. I think there's some neutral density filters in here. There may be some other filters that are for specific types of chemistry where you want to only look at certain lights. A lot of times you fluoresce at one frequency and measure it at a different frequency, so That may be what these, like I said, I don't have any documentation on this thing, so that may be what those are. There is a photo interrupter on this filter wheel, so I had to figure out, there's like single pulses and then a double pulse, and then you can figure out where 0 is. Then I had to figure out how many pulses per revolution everything needed. But yeah, it was a really fun project.